So this course is called Abstract Harmonic Analysis, and it is difficult to say in few words what is it about. More or less it is related to what is called harmonic analysis in groups. So when we have a group structure, then we have the family of shift operators, and with this family we can relate some spectral statements and some spectral properties and so on and so on and so on. But the subject is very large and very ramified, and so I will touch upon only several topics maybe in the field. Surely I start with some basic things, that is, we will start with the construction of the harm measure on an arbitrary locally compact, not necessarily abelian group, maybe non-commutative. And then I will switch to commutative groups, but also we shall study something about, in the non-commutative settings, well, something general, say the Peter-Weil theorem, representations of non-commutative groups and so on. But finally, I think we'll finish with something that will be quite commutative. Okay. So who of you knows what the harm measure is? Okay, so at least three. And you all know the complete construction? No, you know the definition only.
Definition?
You know the definition. Who saw the complete construction? Yes.
What construction? It is by some.
Yes.
Filtration.
Yes. By some coefficient. Well, so the point is that basically there is some branch point when you construct higher measure. Either you use Tikhonov theorem and take some cluster point, or you don't. You prove that some limit really exists without any cluster points. And so I decided to take the second way this time. Partly because you are here, because when you listened to my course some years ago, then it was with cluster points.
Before this, could you give us some reference and your email address and something like?
Sorry?
Before this, could you give us some reference?
Yes, sure. I'll give. Sure. Sure, but so I can. There is a book where you can find virtually everything. This is a 2-volume monograph by Hewitt and Ross, and it's called Fourier Analysis on Groups. Hewitt. Almost impossible to read because it's very large.
Yes, it's 2 volumes then.
Yes, so it can be read only in the reverse direction. That is, if you want some statement, you find the statement and then you mount the tree of references. So there is another book which is much easier. No, Fourier analysis group, this is Ruzin, Hewitt Ross. Hewitt Ross, this is abstract harmonic analysis. Okay, so this one is very nice and easy. This one is very difficult, but a great amount of material. And also, as to more modern commutative things, there is a book, I don't remember when it appeared, in the 80s of the last century. This is Graham and McGee. And the title is Essays in Commutative Harmonic Analysis. So as to the construction of the Haar measure, you can also find something in some standard texts on measure theory. Say in Halmer's book, measure theory, very old but interesting, and in some other sources. So, okay. Now. Okay, so let's start. First of all, what is a locally compact group? Locally compact group. So first, this is some topological space which is locally compact. And has a group structure. I'll write it multiplicatively, for the moment at least. A group, and moreover, the mapping like this. Is continuous from G cross G to G. So this is definition. There are different schools about this notion of local compactness. When I use it, I mean that this is also Hausdorff space, automatically. Sometimes it is not assumed, and then some pathology may occur. But we shall always assume that it is Hausdorff, then it is normal because locally compact and so on. No topological abstractions of on the level of separation theorems and so on. This condition is a compact way to say that the product and the inverse are both continuous. I may erase it. Now, the theorem which I am going to prove. So the theorem which I am going to prove is that there is a measure mu on G which is non-negative, non-zero, and left invariant. That is mu of y If is a Borel set, this is a regular Borel measure in the usual sense. When I tell regular Borel measure, you understand what I mean, yes? Okay. So this is my goal, my first goal to show you. To construct such a measure, I will need the classical Riesz representation theorem, which probably is known to you for the case of compact sets, but maybe not so much well known for locally compact spaces. So let me state it. Okay, so let S be a locally compact space, and consider the set which I am going to denote this way. This is a space of non-negative continuous and compactly supported functions on S. Then consider a functional phi on this space, which is assumed to be non-negative and additive. Even linear, non-negative, additive, and homogeneous. So here alpha and beta are scalars, non-negative scalars, and f and g are functions from this space. Now, how to understand this notation? This C is for compact support, and this is because they are all non-negative. So consider such a functional, then there exists a regular Borel measure mu on S such that phi of f is the integral of f against this measure. Regular non-negative. Okay. Of course, we can also go in the other direction. If you have such a measure, then this formula defines the functional.
Okay, so every time we consider the compact spaces, we silently assume Hausdorff property?
Yes, yes, yes. Sure, I told this. Compact includes Hausdorff for me. Okay. If you know the Riesz representation theorem for compact spaces, then you may see that this is something relevant, because when S is compact, then every such functional is automatically continuous, because its norm simply is equal to its value on the function identically equal to 1. So it is continuous, and then it is represented by a measure. Here the difference is that to define, let's abandon this condition that the functions should be positive. Let's consider only continuous functions with compact support. Then to define a topology, a proper topology on this set is a somewhat tricky matter. This is something like the space of test functions in the distribution theory. So this is some inductive limit, and I don't want to discuss this here. But if we restrict ourselves to positive functions, then you see here I don't demand that phi be continuous, but if we introduce this topology, which I didn't explain what it means, but if we introduce it, then it turns out that such a functional is continuous automatically. And so it is represented by a measure, and moreover, if you know the Riesz representation theorem for compact spaces, then you can prove it in a fairly easy way. Simply consider a compact subset of S, and consider all functions whose support is included in S. Then phi generates a functional on the space of all continuous functions on this compact subset. Okay? And it is represented by some measure on this subset. And then when we consider an expanding net of subsets, of compact subsets, then we obtain a net of measures which are coordinated on each subset. When we take this construction for some subset and then for some bigger subset, then the new measure will coincide with the old one on the smaller subset. And so we obtain a measure on the entire space, and the point is that a positive functional on the space of continuous functions on some compact set is always continuous, because
maybe here we should assume this to be sigma finite.
Sorry?
Sigma finite.
It is not sigma finite. It may happen to be not sigma finite. If the group is very, very large, it may happen to be not sigma finite. If the space is very large, it may happen not to be sigma finite. So the simplest example is some discrete set which is uncountable.
Yes.
And the counting measure, it is not sigma finite.
We also have,
But okay. So when the space is metrizable and countable at infinity, it is sigma finite, but in general it may fail to be there. So this is a proper question, because I thought that you can prove this from the classical Riesz theorem for compact spaces by applying it to wider and wider compact subset of S, but there will be some tiny problems with related to this absence of the sigma finite property, so something about measurability and so on, because in fact this union of compact subsets, it is not countable, and so it should be proved separately that the measure of every set is determined by the measures of its intersection with compact subsets. Well, so there is something there. I didn't tell everything, but still let's believe. Well, you can take any say any large book on measure theory, or probably any large course of functional analysis, and there it will be proved that there is such a theorem. So anyway, we want to construct an invariant measure, and for that we want to use this representation theorem, and to have such an invariant measure, we should construct some functional additive and homogeneous. And which is also left invariant. This means that phi of f superposition with say and this notation L sub y to the power minus 1, this is the following thing. So L y, this is simply as a shift. Simply as a shift. So this is a shifted function. And we want to construct a functional which is non-negative, homogeneous, additive, and invariant under left shifts. I write here y to the power minus 1 just for convenience, because in the course of the proof it will be convenient to have minus 1 here. So when we construct such a functional, then the representation theorem will provide a measure on G, and this measure also will be left invariant. So I don't want to explain this, but it is easy. Yes, it is easy. So please believe, or prove yourselves that is automatically if it is left invariant on continuous functions with compact support, then it is left invariant on the level of sets. So So we must construct such a functional which should be homogeneous, additive, and left invariant. And for the moment, we don't know if even, and of course non-zero, of course non-zero, of course non-zero. Even at least one such functional exists. But it turns out that it is fairly easy to construct functionals with similar properties if we drop the condition of additivity. And so, so let me single out some properties. So consider a functional I from this space. It is left invariant if I may for the moment write here not without power minus 1 because, well, more or less it is the same, but at some point it will be easier if you write this power, but okay, let's right now use the following. For every function f, second homogeneity property. Lambda is a non-negative real number. So this we retain. Next, we shall consider functionals which are not additive, as I told, but we need subadditivity. And the last property is monotonicity. Sure, all functions here belong to this space, and let's distinguish these four properties and consider the set F, the script F, of all functionals I with these properties 1 through 4. So this is F, but as I told, we need a linear functional, in fact, and so L, this is the set of additive functionals, satisfying one, so the left invariant, and homogeneous, and 2. So we don't know if there is something. For the moment, we don't know if there is something non-zero in L, and our task is precisely to construct a non-zero functional. Okay, all of them are positive. All of them are positive, sure. So our task is to construct some non-zero functional L. Let me remark that in any case we have this inclusion because subadditivity is clear and monotonicity is also clear since we can simply write if f is smaller than or equal to g, then and we have a functional L, then this functional on g is equal to this functional on g minus f plus the same functional on f, and this function is non-negative, and all our functionals take only non-negative values, so clearly this is greater than or equal to g of f. So any additive functional. Sorry?
Could I turn on the light, please? It's kind of dark here.
Good.
Can I turn on the light?
Sure.
Thank you.
It's better, yes?
Yeah, thank you.
Okay. So now I want to show you many functionals in this space, this class F, and after that we shall construct a functional in L, which is non-zero. But first I want to give a more precise formulation of this theorem about the existence of a Hard measure, because first it doesn't only exist, it is also unique, and this should be included in the statement, and also it has some additional property. Left invariant, positive, non-negative, non-zero, additive, and homogeneous. Functional lambda on this space. Next, it is unique. Up to multiplication by a positive constant. And also this functional is strictly positive on every non-zero function. even so. Well, so the main result is not only the existence of a left invariant Haar measure, but also the uniqueness. There is only one functional of this sort. This, in terms of measure, the last condition can be restated as follows: that all open sets have a non-zero measure, maybe infinite, but non-zero measure. So this measure doesn't vanish anywhere on a substantial set. Okay. Now, let me start the construction. So, some functionals in the set F. So I can produce at once some additive functional, but some subadditive functionals can be exhibited in an easy way. Fix some function G in our space. That is non-negative, continuous with compact support, and let it be non-zero, not identically zero. For F in the same space, define the following quantity. So I sub G of F, this is the infimum of all S. I'll write this in a somewhat tricky way, maybe, but it will be convenient later to write this in such form. So the infimum of all S with the following properties. These S are non-negative, and also there is a finite set of points in G, so that there are some coefficients CA, also non-negative. A here runs over this finite set, such that my function f is dominated by the sum of the following things: CA, G, superposition with L, A to the power minus 1. And the sum of C alpha is less than or equal to S. So this way is somewhat tricky, because what happens really is that we seek all majorizations of this sort. For each such majorization, we calculate the sum of these coefficients. And then we try to find the infimum of these sums. And if you think a little, you see that it is the same. So we find here the infimum of all upper bounds for such sums of coefficients, where the coefficients are such that my function f is dominated by the following finite system of shifts of this function g. Okay? So this is the definition of my functional.
Why do you need the s this zero condition?
Which?
I mean, infinite.
So this functional is equal to the infimum of all s with the following property.
Yeah, but why do you need that s is at least zero?
Well, okay, I may erase it. Okay, I may erase it because it is written here.
Yes.
It is written here. You can read this here. So you may erase it, and you may leave it also because this doesn't change anything. So it is written in two places. Okay. Well, first it's clear that such systems do exist, because my g is a non-zero function. A non-zero function. So it has uniform norm, and this uniform norm, the supremum norm, is non-zero. So take the open set where g is greater than half the supremum norm. G is greater than half its maximum. Then this is an open set. And my function f has a compact support. So a finite system of shifts of this open set covers the support of f. Okay? And on every set of this system, this function is greater than 1/2 the norm of g. So if I take sufficient large coefficients, then they dominate. Okay, f. So I think I should not write anything.
Could it please, maybe I understand maybe. Did you say that you take like this open?
So you have your function. Here is a function g. It is well. So you just take the set where it is greater than 1/2 its maximum.
Yeah, I understand. I mean,
Then you take all shifts of this set by elements of the group. So a finite number of these shifts covers the support of f, because the support is compact. So on each such shifted set, the shift of g is greater than half its maximum. So if we multiply this by a sufficiently large constant, then we obtain something which is greater than f on this set, and so the sum will be greater than f everywhere.
You want to prove that this cannot be infinite?
Yes. It can be infinite, because, of course, but since the support of f is compact, there is a finite number of shifts of this set that cover the support and so on. Okay. So this is always finite. Such coverings, such inequalities always exist. So this is a well-defined functional, and what is interesting, but it's clear absolutely, that always this functional belongs to the set F. Automatically. So, okay, what do we need to ensure this inclusion? We need that this function will be positive. Well, this is clear because, well, okay, this is infinite of some positive numbers. We need this functional to be homogeneous. Of course, if we multiply f by some constant, some positive constant, then everything here is multiplied by the same constant, so it is homogeneous. So we need that our functional be subadditive. Surely if we have two functions, f and f prime, and each of them is dominated by a sum of this sort, then their sum is dominated by the sum of all involved functions, involved shifts of our function g. And, well, okay, it's clear that f of this function of the sum of two functions is less than or equal to the sum of values of functional functions. And also, we need that this function will be left invariant, but it is clear from the definition. If I shift f by some vector, some element of g, then everything here becomes shifted by the same element of g, and so we obtain the same. So this functional is an f, well, but still is not an L. So we still have some work to do. Let me start with some properties of this functional. So the plan will be as follows. I will prove something which is easy. Then I will state 2, maybe 3 lemmas without proof. Then I will show how these lemmas imply the uniqueness and the existence of the functional we are looking for. And after that, I will collect the proofs of these lemmas, which are not very hard, but it is not quite pleasant, unfortunately. Okay, so the first fact. For every functional g in f, so for every functional that satisfies our 4 properties, we have the following inequality. So g of f is dominated by j of f, ig of f times j of g. So this is for every f in my space of test functions. Well, the property itself is fairly clear because you see, look at the definition, even I don't want to write anything. So look at this definition and apply this functional j to both sides of this inequality. Then, since j is monotone, its value on f will be dominated by its value on this function. So g of f is less than or equal to the value of g on this function. So g is subadditive, so we can replace g of this function by the sum of g of these functions, and it's homogeneous, so we can take these coefficients out of g, and then j on these functions is translation invariant, so this will be one and the same thing. So from this inequality it will follow that j of f is less than or equal to j of g times the sum of CA. Well, And so this is dominated by S, and when we pass to the infimum over S, we obtain what we need. Okay? So we have proved this inequality. And it is interesting to remark that we can, in this inequality, for example, we can take for G the norm in the space L infinity, the usual supremum norm. This is a function which satisfies all these properties. Okay? So if we take this norm for J, then what do we obtain? So we see that this quantity must be positive whenever f is non-zero, in particular. Yes? So. Also, look here, and now consider a general functional J, and we see that if this quantity is strictly positive for some f, then this quantity also must be strictly positive for every function J. Okay? Since our conjectural linear functional, which we are looking for, also satisfies, also lies in this class F, we see that we should not take care of this last property. Every such invariant function, which is linear, will be positive for all negative, all non-zero functions. Okay, so this thing has already been proved. Okay. Now this all is easy, and let me formulate some lemmas. Well, I want to erase the definition, though this line will be useful to us at some moment, but I will reproduce it. Okay, so first lemma. So all such functions are only subadditive, and we want to obtain something additive. When we obtain something additive, we are done. But it turns out that they are almost super additive. So they are very close to be additive in any case. So the statement is as follows. For every finite collection of functions, and every r which is greater than 1, it should be sort of something very close to 1. So we take something greater than 1, but very close to 1. Okay, to state this I need yet another notation. let probably not. Probably not. No, I need so notation. Let V be a neighborhood of the unity in our group G. So this is a unity of G. Then this notation P of V is reserved for the set of all functions say H in our space whose support is included in G and that are not identically zero. Okay. Also, we need yet another thing. V. Of course, V. V. Support H is in V, of course, V. In G it is automatically, so it is not a condition. Simply, I'm confused V with G and okay.
Okay, if we ask H to be compactly supported.
Compactly supported with support in this neighborhood of V.
Yes, but I mean, if we take CC of V, then we can drop the condition.
Well, okay. Well, but V mustn't be compact itself, so we ask H to be compactly supported, to have support included in V. This is an open set. V is an open set, not necessarily compact neighborhood, open set.
Yes, I know, but still we consider CC of V, so
of G. Simply I'm confused between G and V in this formula throughout. So okay, and also we will need in future the set P star of V. This is the same, but moreover H of Y is equal to H of Y to the power minus 1. For that, we also need that V be equal to V to the power minus 1. This is not a restriction, in fact, because such a neighborhood of unity is called symmetric, and there is a base of symmetric neighborhoods of unity in every locally compact topological group. Simply you take an arbitrary base and take the intersection of V and V minus 1 for every V in this base, and so you obtain symmetric neighborhoods. And so for such a function, for such a neighborhood, you may also consider symmetric functions in this sense, which satisfy this property. It also should be noted that if we have some function in this set P of V, then we can consider the function maximum of H of Y to the power minus 1. In this case, when V is equal to V minus 1, this will lie in this set P star. So in what follows, we often will construct something in this set, but it should be kept in mind that very often this enables us to construct something similar in this set, just applying this simple procedure. In each particular case, it will be clear that this simple procedure leads to the same, to an object with the same properties we needed here. So, okay. So I started to formulate a lemma. Now we have some functions here, and so for every functions in this space and every R, there is a neighborhood V of E. So maybe it is useful to introduce some notation, probably that let's denote by this script U the collection of all open neighborhoods of unity in our group. So just for me to avoid writing the word neighborhood of unity every time, so there is a neighborhood of unity, so that we have the following: e.g. of f1 plus and so on, e.g. of fn is dominated by R times e.g. of the sum for all G in this set P of V. So you see, we are looking for some additive functional. This functional is not additive, but something very close happens. We have this inequality where R should be thought of as very close to 1. But this is true not for all functionals of this sort, but precisely as it is written. So for every functions and every R, we can find a neighborhood such that you have this thing. So this is first lemma. Now, the second lemma, it is something reciprocal to this inequality. It looks like something technical, but still I will state it, and we believe that this is true. So for the moment I meet the proof. I will postpone it till some better time. And here lemma 2. Lemma 2. For every f in my standard space of test functions, for every r greater than 1, there is a neighborhood of unity in our group such that, well, it is somewhat tricky in the statement. For every G in P star of U, so I need a symmetric function with support in U. There exists yet another neighborhood of unity such that we have the following. We have something inverse, something close to this. So IG of f g of g is denominated by r times ig of f. Now I must say for which functionals g this is true. So this is true in two cases. One will be used in the proof of uniqueness and the other in the proof of existence. So for the uniqueness we need that this is true for all g that are additive. And for the existence we need that this is true for g equal to I h, where h is in the set P of W. Well, so we have the converse to this inequality with some error. And this is true first for all additive functionals. And second, for all functionals I sub h generated by functions, non-zero functions with support in this small neighborhood W. Okay, so you can remember just that under some conditions which are listed here, we have the converse to this one.
What are the pointers? I mean, does it hold for any j, or does it hold for such j's that are in
for any g. For any g.
For any g in like
for any g in this. So the logic is as follows: we take a function and a number, then by this function, this number, we find some neighborhood, so that for every g supported in some neighborhood, non-zero and symmetric, we can find another neighborhood, so that for this g, this is true in two cases. This function is equal to what is written here, and second, this function is additive.
So in the first case, we do not need to take W.
In first case?
In the first case, we need not to take W.
We don't need to take W, but you know, it is convenient to formulate this way because the conclusion is the same, and so in this case, of course, this doesn't depend on W. Sure. So it looks something strangely, but I told you that the entire argument will split. So this is needed for uniqueness and this for existence. And of course, this part which is needed for existence is somewhat more difficult than this one. And simply, well, probably the proper logic is as follows: to prove this and then to remark that, okay, but if you have additivity, then everything goes even easier and so on. But we'll see that later. Okay, well, what do I need? Probably that's all. I need. Okay, so let's take this for granted. This lemma and this lemma, and also we know this inequality. Okay, and now I want to finish the proof of the theorem by using these statements. First, fix some function phi well in every time when I pronounce phi or phi, I wonder, some of these two ways is American and the other is British, but I don't remember which one. It seems to me that phi is British and phi is American. Okay, you don't know.
I'm sorry, I said phi.
Phi?
But you are American. Kind of.
Okay, so I'm not sure I will be consistent with that all the time. Well, okay. So this function will be fixed once forever, okay, and it will be non-zero. Non-zero. P of G is G is also a neighborhood. So I mean that this is a function. This is a function of this space, but it is not zero. It is not identically zero. So if I write this instead of this, then I also use the condition that my function is not identically zero. Okay. Okay. Yes. Okay. So let's fix this function. And now we normalize our functionals I sub g. So for every g, which is also in this space, also not identical to zero, of course, we put lambda sub g is equal to 1 over ig of phi ig. So consider this normalized functional. And I claim that this is dominated by the functional I phi. So this is precisely this inequality. Simply, the notation is somewhat confusing because this is equivalent to what? Ig of, say, u less than or equal to Ig of phi, I phi of u. This is this inequality, and now you easily recognize it here when you change the notation. So, okay. Yes? Who is who? G, who is who here? Phi here plays the role of G here, and U plays the role of F. Okay, yes? So, okay. So we have this. And now we use this lemma 2. We use this lemma 2, this complicated logical chain. We fix also some r greater than 1. Then there exists a neighborhood u. And now I mark its dependence on the objects mentioned here. It depends on f and on r. So, okay. Such that everything which is written here is true. That is, well, but not only for, well, okay, I write what I need. So for every G which is invariant and has support in U and non-zero, there is another neighborhood in U, W, such that we have two inequalities. First, G of F is dominated by IG of F, G of J, and this is dominated by R G of F. So this is simply these two inequalities concatenated. Yes? But also we need the same. We need the same, let me write it here, for phi. So we have also this inequality. Simply just apply this to phi instead of f. This will lead to somewhat narrower neighborhood, but, well, not matter. Okay? So we can combine these two things. Well, I want to erase this lemma 1. I will need this, but it is so clear that I think you remember, and you may avoid to have it visible when I shall use it. Well, and again, for which J is it true? This is true first for all additive J, and second for all J of this form. Okay, and now let us divide this double inequality by this one. To divide, we should write it in the reverse order. Okay, so we divide this term by the biggest term here, then we divide this term by this term, and we divide this term by the smallest term here. This results in the following thing: R to the power minus 1 lambda G of F less than or equal to G of F G of phi, and this is less than or equal to R lambda G of F. Okay? So let's look carefully at these two inequalities and understand that really the things are as written. So when we divide this term by this term, we obtain G of F over G of phi, which is here, and this is dominated by what? By the quotient of this term by this term, which is precisely lambda G of F. Okay? So we see that we have this inequality, and with this inequality it is the same. So we must divide this term by this term. We obtain R. Well, okay, no, what? So we have obtained this inequality, and for this inequality we divide this term by this term. By this term we obtain some confusion. Yes, we obtain R times this thing, And this will be dominated precisely by lambda, minorated by precisely by lambda g of f. So okay. Everything is okay, yes? And this is true, first, G additive. And second, G is equal to IH with H in P of W. Okay. Now we use this to prove uniqueness. We use this to prove uniqueness. Okay. What do we have here? We see that, in fact, if G is some additive functional, then this quotient lies between these two things. No.
What's the problem? You just take R going to 1.
In fact, yes. R is very close to 1. This is precisely what I want to say. I want to say that this thing is determined by something permanent, because lambda j is some concrete, some specific functional. Lambda j is some specific functional, very concrete. We have fixed f, so we obtain this lambda j. And here there is no j. We can fix j, fix phi, and we see that for every additive functionals j and j prime, these things j of f over j of phi and j prime of f over j prime of phi are the same. Okay. And this means that these two functionals are multiples of each other with some positive constant. Yes?
Yes.
So uniqueness follows from this inequality for additive functions J. Well, and now we use this second case to prove the existence. Well, it is something like 15 lines, but still it is somewhat tricky, a little bit. Okay, so we have that inequality. What can I erase? Probably this thing can be erased. Consider among the set. This is a set Again, this means simply that G belongs to a space of test functions and is not identically zero, such that there exists a neighborhood W in U for which lambda G of F is dominated by R lambda H of F for all H in P of W. So consider the set. In fact, we shall see that it has something to do with this inequality. Oops. Something with this inequality. Let's look at this inequality. Let's look at this inequality, and we know that this thing is true for all functionals of this sort. You see? You see? This is true for all functionals of this sort. Well, okay. And here, what do we have here? Here, G is symmetric function in this set. So